So continuing from the last video, so the control of our nervous system, and there are like these tools that we use in our nervous system. So for push and pull, it's not necessarily a literal like push and pull of like of object, but we're talking about like the excitation and inhibition of like neurons. So we're pushing and like pulling, and like we can like kind of direct the movement or direct the activity of our levels to kind of control our system. And then feedback. So feedback like system, there's like visual. There's a visual feedback. When we're picking up some object, there's a visual, and then like we sense it from our sensor, like from our fingertips, the pressure, the texture, the shape, and then the location of our like arms and hand, and we all feel that, and then and it kind of goes back and forth, and using those sensations we kind of adjust our movement. And there's some like they say visual feedback, but also like we can still pick it up, pick like a mug while like closing our eyes. So there's some like other, without visuals we can still kind of do it, and it's kind of like complex. But also for the classic example, like grabbing an egg, like we have to just hold it like just enough so that we don't drop it, but also we don't like crush it, kind of thing. So there's like a visual, auditory, somatosensory, and if there's like a lot of like complex feedback going on. Actually, one thing that's interesting, so when we're like looking at something and this LGN, the feedback signal from the thalamus, so like they go into like our brain and cortex and thalamus, and then they do some type of processing, and they give the feedback back to the LGN, the main receptor or the visual processing neurons. And actually that feedback is stronger, the feedback from thalamus is stronger than the just direct signal from the eye. So that's really interesting, and something is going on under it. Modulator versus driver. So I mean, like there's in the visual system, you have this receptive field that's like going in to LGN, and then there's also like there's different modulators. So this driver's the main information, and modulators is like they're affecting the relay and like processing of the driver input. So like they do some kind of processing, and then like give the feed signal back to it. And I guess the main difference is that like drivers, the modulator is a little more complex than driver, and they're not just like 100% like trying to excite it. Like for retina, it's either like on or off, or there's a like bright light or like less bright light. But like modulating is more of a controlling smoothly so that like the system can function. So it's a little more nuanced and complex depth to it than driver. Notation plasticity. So this bottom we show like with the repetitive stimulation, there's like less and less like response to it. So stimulation. So after one stimulation, it kind of goes down, and then it goes down, exponentially decrease. But there's added components of the stimulation, and sometimes it happens like that. So this is depression. Also, sometimes they just like gets more excitatory, and it's called a facilitation. So this is depression facilitation, and it kind of delves into like the synaptic plasticity of that it remembers what had happened in the past and use it for the current response to it. So that was our previous one, and then to the new one, linear system control basics. So what do you mean by controlling a neural system? So the classic example in engineering is we have some sort of actuation, and it goes through the system, then we have some sort of output to it. So it could be like for controlling robot arm, we give some sort of input to it, and then it changes the signal, or like use that signal to correct this like position of the arm or something like that. But in our neural system, we are going with like this optogenetics, and then we use optogenetics to excite or depress the neuron and affect their firing rate, or we can affect the neural circuit, and then even affect the synchrony of how they fire, how the group of neurons fire together at the same time. And there's electrical stimulation where it's stimulating large neural circuit, and then it goes affect the oscillation of the local field potential in the area. So we're going to go over open loop and closed loop control. And the MIMO is multi-input, multi-output. So we have the open loop control, so we have some input, and it goes through these functions, and then we have some output to it. So we have this actuation, but like how do we know like what to do, to what kind of actuation to give, right? So we have some desired like output, right? So you want to do something, you want the robot to grab an egg or an apple, let's say, and then you give it to that desired input to the controller, and controller converts the intention into some way of actuation. So it could be that like, like move your arm to the right by like 5 centimeters or something, and the system like converts that into like electrical signal of, okay, like put that into like electrical signal into motors, and then we get some desired output. So we need some kind of controller to like convert the desired output into an actuation into the system. So this is an open loop control, but the closed loop is a little different in that they have like extra feedback system here, and have sensors. So we measure some kind of output, and then it goes feed back into the input here, where it takes the difference of what we desire and what we have, the output, and there could be the error, and then the error is fit into the system again. And it's a good system because in biology most models are not that great. So this open loop control will work perfectly in theory, assuming that we have perfect models, so we can kind of feed something in and they will just do the exact thing that we have intended to do. However, it's not like that in reality. There's going to be robot arm example. There could be a wind or some kind of maybe resistance within the motor or bearings, or especially in biology there are so many like noises, and we don't really have a good understanding of it, so we don't have a good model to start with. So if we had done open loop control, it would not work, and there's no way to correct it, so it would just stay crappy. The closed loop control, even though the model is crude, feedback can kind of compensate for it, and that's why in biology this closed loop control is very important. And it's used in a lot of different systems, like the aerial, like aircraft. But open loop control is a little bit simpler, so we can talk more about it. So we have some sort of a desired or like a UT that we're putting it in the system, and then like we get some white output YT, and we can put that in these linear systems into the time domain and frequency domain. So let's say let's say tau is 0, then so like we're at the edge or boundary of this integral, and then it will be G0, and then use T, and sure, that's great. And if tau is 1, now it would G1 and U T minus 1. And G1 is like the present, like the time constant 1. But the U T minus 1 is, we're talking about the past, right? Because T minus 1. It has the present component and past component as well. And we have those are like the convolution of it. Here G represent the representation of the linear system, but this is kind of complex and a lot of integral component working stuff in it. So if we using our transfer function to make a time domain to transfer a frequency domain through a Laplace transform, and this is like a simpler linear math where it's just y equal g times u. It's basically like y equal ax. S here is complex variable, so it makes the math easier. So this can be, and if you convert this integral into just like a sigma, so the sum, and you can convert it this way as well. This is like the MATLAB code that could be used. This impulse response estimate is the G, and data here will have some kind of input and some sort of output. And you can kind of, honestly, I don't really understand this. An open loop control relationship, response and transfer function. It's like, yeah, math is easier in Laplace, like a lot easier than this. This is some example of the known like time domain and like the frequency domain. Okay, this stands for proportional integral derivative, which we'll cover later. So come back to this denominator polynomial and numerator polynomial as is the polynomials, and we can like do this like repetitive math with Python, and like they will crunch number. And if you solve it out a little more, it kind of looks like that. And the roots of denominators are poles, and which are the same thing as eigenvectors, and it really shows how the system will respond to an input. So whether it will kind of think of like dynamics like system with like phase diagram, and it can show it will oscillate or like converge, or it will be like stable system. Kind of look like so. So this is a real axis, imaginary axis, and on here where it is a negative, or like on the imaginary 0 on this negative real axis, then it's just stable and just converges to 0. And when the real is positive, then it just gets bigger and bigger, and it's unstable. But if you add the imaginary component to it, and it will like have oscillation and get bigger and bigger with oscillation. The other way, if you add imaginary to this stable system, it will still stable, but it will have oscillatory. So imaginary adds oscillation to it, and real really determines the direction of the growth. On open loop control, the transfer function gives you everything for the linear system. So this G represent gain or scaling, and then some sine function WT plus the phase shift. And then this phase shift is like the angle of this J omega. So we're doing a lot of the linear stuff, and reason being is, and yet nothing in biology is linear. Is truly linear, but if you break it down into like small like range, it is close enough to linear systems, so we can put together a bunch of those like linear systems to kind of model the whole dynamics. And so we just need to milk out as much as possible from the linear system, because nonlinear is super hard. And one of the example is like Fourier transform, because Fourier transform is really like any like type of signals, like let's say we have, okay, this loop can't happen, but let me do it. Let's say we have this, and it looks crappy, but like this can be like modeled with like addition of this, and then addition of this sine signal, and addition of superfine sine, and then you can like adjust the like we want one of this, we want two of this, we want like maybe 0.5 4 of this, and we can just keep adding like different sinus signal to create this some complex non-sinusoidal looking output signal. So we're adding a bunch of linear system here to present the non-linear looking signal. So goes hand in hand with like we gotta milk out as much as possible from linear system. And this classic Bode plot in frequency on the y-axis, and then on the magnitude here. This is magnitude, the signal, and then this is phase. So here, like up till this part is pretty much like stand still. After that, as it goes higher, like the frequency is like isn't like negative, so gain, which means it's like minimizing the signal. It's a low pass filter, as you can see. Apparently on the speaker has they have a Bode plot to show like what kind of sound they like can, how they like process it and whatnot. And good speaker would not mess with any of the sound. It will just play the whole thing as it is, so it will have like a flat Bode plot. Anyway, coming to the open loop control, inverting the plant. So you assume we have a good model and we can invert it. So all it will do is just like so right now the output is the output y is equal to u times g, the desired input. But if you have 1 over g, then whatever desired goes in, and then it kind of gets canceled out in here. So it means the desired input will be, or the desired is exactly the same as the output. But in reality, there's a bunch of noise and others, and the model's not good enough, so it's not going to work. But that's the theory, or that's the idea behind it. So per model, there's disturbances, noises, and then this model itself can change over time, and so it doesn't really work well. So we have to go back to closed loop control, and it's a thermostat is also like closed loop system or like cruise control. So if the temperature is too high, then what then the desired temperature, then you like bring the temperature down, and the other vice versa as well. This is like a power network in Europe, so they have to regulate the distribution and generation of the electricity to a changing demand. And during the control in biology, in like cells, there's like a bunch of different like signaling pathways and how they produce a bunch of stuff. So it's essential for life. It's a block diagram. So now we have added this feedback part, and this is a -1. It's negative because it's like we have to subtract from the desired, and so you can fit that becomes error. So with simple like on-off control for like HVAC, so we have this error. So we have some desired like thing at here where error is equal to 0, and then if error is like here, so let's say for heating, like you set the temperature to like 70, and but now it is like 68 degree, then 70 minus 68 would be like 2, so we just like here or something, and then okay, now then you have to turn it on to the max, and then vice versa. If it's too hot, you keep it at minimum. So that's simple on off, but like maybe we can like we want to control the rate of change of temperature. So if it's super cold, then you want to heat up as much as possible, and if it's not that cold, then you just want to turn up the heat a little bit, and then you can have this like a linear function. So like the more the bigger the error is, we can compensate it for larger. Integral feedback drives steady state error to 0. I honestly didn't understand this, so let's skip that. Derivative feedback, so we can like change it, see how the error is changing over time, and if it's changing so rapidly, we see the trend and we can kind of anticipate what the future error will be. And right, so put the brakes on if error is decreasing, because the error is going up too quickly, so we don't want it to be full blasting until right before it reaches the like the error 0. So we can kind of like slow down so that it doesn't overshoot. And if the error is growing rapidly, like exponentially, then we want to just like halt it as much as possible, like before it gets too big. So then you will kind of preventative measure of increase the feedback stronger. So derivative feedback. So we combine all of those integral, derivative, and the proportional, and call it PID control system. So it kind of looks like that, but if you're in the Laplace domain, it looks like this. And then if you just divide it by s or multiply by s and then put it on here, like kind of looks s squared plus s plus constant, and that becomes g, which is the controller. And this is like the real system here. And we can take this, and this could be modeled as this equation, and it's a closed loop transfer function. So we can see overshoot, steady state error, rise time. So measure of how do you like measure this? Stability, like so modern fighters are actually not as stable as like the past, like previous generations, because they use computer to control it to make it stable. And if it's unstable, which means they can like change their like maneuver rapidly because there's no opposing force that makes them kind of stay in the stable positions. So fly-by-wire system allows us to happen, but stability, so steady state error, well, maybe like this is for some like biological system, it is not okay to have steady state error because it's like biology and like medicine, so it could be dangerous. So we need to control it as well, the rise time and speed, like how fast do we need to correct it, right? Some situation, the time is of the essence. General tracking, it's shown over here. There's given the route, like how do we like make the optimal route, disturbance rejections. So like things are going to change, and there's going to be noises for cars, for example. Tires get degraded and get smaller, so it's that same revolution. There's not going to go as much of a distance, depends on the number of people in the car, etc. So there's going to be different like noises and factors that's not accounted, and then we have to compensate for it. So that goes with the robustness of their control system on how to make it stable. So closed loop control, it works well in general, and even if the model is not great and entirely like accurate, with the good feedback system, we can kind of make the control system work. So that's a great thing. But it's not that great in multi-input, multi-output system. So for example, like this, there's like, think of visual system, and there's like multi-pixel image that's being shown. So multi-input, and the output, there's a bunch of different like visual neurons, and they all like firing at different rate and synchrony, and like how to predict that or control it. And it's really hard to do it with a this closed loop system. In this case, we use like latent variables.